Okay, it's 1 o'clock. It's Friday afternoon, so let's get started. Welcome to PhD Defense for Artem Alexeyev. He will be defending his thesis, which was called Modeling of Salinity Effects on Water Flooding in Petroleum Reservoirs. And that's also the title of his talk. Yes. So, biggest welcome, of course, to the candidate, who's the expert in this subject. And of course, we would also like to welcome the three examiners. So we have Professor Eric Mackay from the Department of Petroleum Engineering here at Watt University. Roman Berenblom, who's the Research Director at IRIS Research Center in Stavanger, Norway. And Sissel Marie Nielsen, who is the Senior Researcher at the Center for Oil and Gas, Danish Hydrocarbon Research and Technology Center from DTU, who's the local member of the committee. And the procedure is as follows. So we have 45 minutes assigned for the candidate to present his work. And then we will continue with questions. We'll have a very short break after that. And then we'll have some questions from the examiners. If anybody during the course of the lecture is interested in asking a question, please come and tell me during the lecture, and I'll put you into the program. We will start with Professor Mackay, and then Dr. Berenblom, and then Dr. Nielsen afterwards. And we will say that the whole proceeding should take 3 hours maximum. It needs to be finished by 4 o'clock. And as soon as Artem is hooked up, wired for sound, then we will commence. So over to you.
Good day, everyone. Today I'm going to present my PhD study on the modeling of salinity effects in petroleum reservoirs, which was carried out at the Department of Chemical Engineering and Center for Energy Resources Engineering, CERE. This is a brief overview of the today's presentation. I will start with the introduction into the subject. Then I will continue with the Buckler-Leverett model, which is a conventionally applied model to describe macroscopic flow of two fluids in porous media. I will continue. Oops, I'm sorry. These are the long slides. So this is the overview. The next of the presentation is divided into 3 sections, which are related to 3 core studies of the thesis, which the first addresses the effect of mineral dissolution, the second addresses the mobilization and flow of oil ganglia, both on micro and macro scale, and the third study addresses the analysis of the smart water experiments, the numerical analysis mostly in carbonates. So let me start with the introduction. Water flooding in petroleum reservoirs is an effective and low-cost method of improving recovery. The idea is very simple. We inject water, and it displaces oil from underground, and also it gives pressure support to the reservoir. And the problem is that significant amount of oil still remains trapped inside the reservoir, and the major task is to reduce these amounts. So in order to solve this problem, enhanced oil recovery techniques are developed, and there are some conventional EOR techniques such as chemical, thermal flooding, or the gas injection. And also there is a number of emerging EOR techniques which are currently extensively studied, which includes microbial injection or smart water flooding. This study is mostly concentrated on the smart water flooding and effect of brine salinity and composition on the efficiency of the recovery. So smart water can be defined as deliberate modification of brine composition in order to improve recovery. And its application can be very well illustrated by the Ekofisk field. The initial recovery was estimated to be 17%, and then water flooding started in 1983. The estimated recovery was increased to 46%, but the efficiency recovery was much higher than it was expected, and the expected recovery was again changed to 55%. Nowadays, there are some people who claim that if we optimize the composition of the injected brine, we can produce additional 10%, which is a huge increment and will benefit. Potentially, smart water nowadays is applied in sandstones, mainly low salinity water flooding. It's also applied in carbonates with regard to seawater flooding. And recent experiments also demonstrate that low salinity water flooding can be applied at least in some of the carbonate reservoirs. A large number of physical and chemical interactions should be considered when dealing with smart water flooding. This includes rock dissolution and precipitation of minerals, also mobilization and migration of fines, change of interfacial tension, and wettability alteration. So there is no common agreement which mechanism contributes to the smarter effects more. That's why the following motivation, it explains the motivation for this study. I mean, there is no clear understanding what is a primary mechanism, and one of the goals of this thesis is to increase our understanding of fluid-rock interactions in the system. It's also important to come up with the models that can reproduce qualitatively and quantitatively the behavior of smart water recovery curves. Also, there is a lack of numerical analysis on the smart water experiments, and in this thesis we would like to introduce some quantitative description that can help on deciding whether some of the smart water mechanisms are relevant or not. So this study is the part of the part of the larger project called the Smart Water Project, which was conducted here at DTU and included both flooding experiments and petrophysical measurements. Here I just want to point out some of the generally applied modeling approaches. So this includes computational fluid dynamics, which is usually applied on the small scales, pore network modeling that applied on the intermediate scales, such as pore ensemble or core plug. And then there are macroscopic models, which include Buckley-Leverett model and more full geochemical models that can account for geochemical interactions and are applied on the core plug scale or reservoir scale. In this thesis, we mostly concentrate on the macroscopic models, but also we consider microscopic displacement and get some ideas from the pore network modeling. So in fact, we consider all the scales, though our main goal is to construct the macroscopic models on the basis of Buckley-Leverett theory. I'm sorry. In order to do that, I need to introduce the Buckley-Leverett theory for those of you who are not aware of it. It's based on the mechanics of continuous medium and usage of mass conservation laws and the concept of relative permeabilities. So it's assumed that porous media can be effectively characterized by the volumetric amount of each of the phases that are presented in there, and the flow of these phases can be related to these volumetric amounts. And this model was successfully applied for studying pressure, thermal, chemical effects. It can account for absorption of chemicals and their dissolution in oil phase. And the central concept here is the concept of relative permeabilities, which is crucial for any kind of enhanced oil recovery modeling, because in general, the flow of fluid is controlled by the relative permeability, which depends on the saturation of this fluid. There are some conventional empirical models that can determine the relative permeabilities in terms of fluid saturation, and they rely on a number of empirical parameters. This slide illustrates the typical shape of relative permeabilities. So the saturation corresponds to water saturation. As we increase water saturation to 0.6, in this particular case, the oil can no longer flow. There its relative permeability is 0, and all the oil that is left here is immobile and cannot flow. And this means we cannot produce it. So how the enhanced oil recovery is modeled? We assume that there is a chemical agent that changes the shape of the relative permeability functions. Usually what is changed is the residual oil saturation for the smart water fluid or the chemical solution. And then it results in the fact that, first of all, oil can flow more efficiently because the relative permeability is higher at a given point of saturation, and also more oil can be displaced just because the residual oil saturation is here. So this is the basis of any kind of enhanced oil recovery modeling. And in this study, we were working on the way to improve it or to relate it to relevant smart water mechanisms. I also have to introduce the Buckley-Leverett problem and Buckley-Leverett solution just for you to understand some of the results that I will present later. The most important feature of the Buckley-Leverett solution is when we inject water in the reservoir, which is initially saturated with connate water and oil, is the formation of the displacement front. As displacement front passes through a certain point, the amount of oil is considerably decreased, while the saturation of water changes jump-wise to some considerable saturation. After that, the oil here, it cannot flow efficiently. So the effective flow of oil occurs only in this zone, while here oil can flow rather slowly. I also need to introduce the chemical problem and the solution for the tertiary flooding, because I will compare my results in the future with this model. So in the tertiary recovery, we inject water in the reservoir that was already flooded with some water. And in extreme case, all the oil in the reservoir is already immobile. So what our chemical solution does is that it decreases the residual oil saturation and mobilizes some of the oil. Mobilized oil is pushed in front of the injected chemical solution and forms an oil bank. And mostly, in many cases, the smart water effect or chemical effect or any kind of enhanced oil recovery effect is estimated by the amount of the oil that is contained in the oil bank, because production of the remaining mobile oil can take considerable time and can be not very effective. There is a number of methods that can be applied for numerical solution of the Buckley-Leverett model or any kind of model that is based on the macroscopic approximation I just described. In this thesis, I used a number of different methods that I use finite volume discretization. The numerical fluxes was calculated according to first order and second order schemes of accuracy. Also, the solution procedure included both coupling of reaction and transport terms and sequential approach where reaction and convection terms are treated sequentially. The integration of governing system of equations was performed numerically using both full implicit, explicit, and mixed methods such as IMPES and so on. Most of this modeling was done from scratch in MATLAB or Fortran. Only the last part, the third study, was performed with the use of external black oil system simulator BOSS, which was modified to account for multi-component transport and enhanced oil recovery effects. So now I will go to my first study, which is the effect of mineral dissolution. In this study, we considered the following effect of dissolution on the porous media. First, it changes the porosity and hence relative permeability. Second, it changes the composition of the brine and also its density, which is usually not accounted for in most of the modeling. And the last thing, it changes the residual oil saturation. The last may seem surprising that residual oil saturation changes due to dissolution, but you need to remember that it's defined with respect to pore volume. So what is constant is not the residual oil saturation, but the product of porosity and residual oil saturation. That's why if porosity changes, and we assume that this solution does not create additionally mobile oil, this will always result in change of residual oil saturation. That's why it's necessary to be careful when this solution is to be considered and relative permeabilities are used. We consider a simplified model where an injected water contained an active solute which was interacting with the mineral and producing aqueous complex. It was described by the first order irreversible reaction, and the reaction rate was treated as an adjustable parameter, which was represented by the dimensionless Dahm-Köchler number. The dimensionless Dahm-Köchler number compares the mass transfer rate due to reaction to the mass transfer rate due to convection. And if the Dahm-Köchler number is low, the reaction can be considered to be slow, while for very large Dahm-Köchler numbers, the reaction is almost instantaneous. So this is the central point of this study. This is why it all started. We wanted to estimate the effect of volumetric non-additivity on the flow in porous media. This is a very simple subject. So when something is get dissolved, the volume of the mineral can change during dissolution. And for example, if this happens in the closed system, the dissolution will cause the increase of pressure if the volume of the particle is larger in the liquid state. So we were curious if something similar can happen in the reservoir and how it will affect the flow. So in order to account for this, we needed a brine density which will be both pressure dependent and compositional dependent. That's why we came up with this linear equation for the density, while the compositional compressibility was determined according to this equation, which required, in fact, only one control parameter, gamma. If this parameter is 0, this means that volumes of the particles in liquid and mineral states are equal. But we performed some calculations comparing the densities, the correlations of brine densities with salts dissolved in it, and this linear dependence, and found out that for most of them, the value of gamma is not 0, but it was negative from 0.3 to 0.9, which means that there is such an effect. But so the numerical modeling was done in Fortran, but the most important features here is that we had to use the coupling approach and fully implicit schemes because of stability issues. When we were trying to compute the pressure according, when we were trying to split the pressure, the transport, and the reaction terms, it resulted in the following problem where we had to decrease the timing step considerably, and this made calculations completely ineffective. So even though the implicit solver is slower per one iteration, it allows for much considerably larger time step, which makes overall performance better. So these are some sample calculations of the model. We can see the effect of slow of dissolution on the evolution of porosity in the system. In fact, the permeability profiles are very similar. And on the right picture here, you can see that for fast dissolution rates, first of all, you need to pay attention that the x-axis here is scaled. So it's only 30% of the reservoir. This is done just to improve visibility of the slide. So the change of permeability on the right slide, on the right figure, occurs mainly close to the injection site, which means that the active solute that causes dissolution cannot penetrate far enough, and unless all the mineral is dissolved in this. And this resembles wormhole formation. Then we performed simulations to estimate the volumetric non-additivity effect, and found out that, in fact, it does not have a significant influence on the pressure. It does have some effect on the velocity of the displacement front. Here you can see that there is some difference between the red and the blue curves, for positive and negative volumetric effects. But again, this effect is very small, and most probably it will not affect anything. Also in this picture, you can see that additional pore volume is created for the injected water to occupy, but this does not, as I said before, does not result in increased oil recovery, as one may expect from looking at a picture like this. So the main conclusions of this study was that non-additivity of volumes and compressibility due to composition does not have any significant effect on the velocity of displacement front. Neither they do have an effect on the magnitude on the pressure in the system. And the second, the most important, is that if reaction rates are high enough, we obtain something like wormhole formation. The second study was devoted to flow and mobilization of oil ganglia. Mobilization and flow, let's say it in the right order. So why it all started? There was an idea that we need to take into account the realistic distribution of phases in the porous media. So the model was initially developed for the tertiary recovery. After the water flooding is completed, the residual oil is left in the system in the form of disjoint drops looking like this, and they can be of one to several pores. And these drops, they remain immobile due to action of capillary forces. You can see the profile of such an oil drop. And if we increase the pressure drop across this oil, the only thing that will happen is that the curvature of menisci will adjust to compensate for this excess pressure. So there are several methods that can be applied to mobilize oil, such as increasing pressure drop, but this cannot usually be realized because first we will just destroy the rock rather than displace this small oil drop, because the capillary forces at this scale is very strong. We also can reduce interfacial tension, but usually it involves usage of chemical solutions, which are costly. And we came up with the following model that absolute water wetness of the rock may mobilize oil. So our idea is the following. The presence of a chemical or an additive in the solution results in its absorption on the surface of the rock, and it changes the wetting state. Due to change of the wetting state, the water films may form on the surface of the rock, which will completely detach oil from the surface. And if this happens, the oil is no longer trapped by the capillary forces. There is a flow of water here, and it may happen that this flow will carry the oil drop, or oil ganglia as we call it. There are several questions in this subject. Is there kinetics of this reaction? I mean, penetration of chemical to this region can be rather slow. And also, how does the detachment occur? What contact angle is required to be achieved for the oil to be mobilized? To study all this, we came up with the micromodel for oil ganglia flow. So what we did, we considered a flow in an angular capillary, represented like this, the oil occupying the center of the pore while the water resides in the center, or in some cases there is a water film completely detaching oil from the surface. And the equations are the continuity and the Stokes equations, while we assume no slip boundary condition at the surface of the pore bodies. And the most important thing is that mutual influence of both liquid, the influence of flow of each liquid on another, is described by the boundary conditions of the liquid-fluid interface. This is usually not considered in most of the models. The mutual influence of fluids is neglected, but it is a central point for the oil ganglia model. And we performed a large number of simulations varying saturation, viscosity ratio, pressure drop, We also tried different boundary conditions on the fluid-fluid interface and changed the thickness of the wetting film. The central results of all this study, we obtained correlation for average flow velocities of each phase with respect to the saturation of the capillary. Here I present only the correlations for the flow of oil ganglia. So as you can see, for the water flow, the linear dependence can be assumed, while we found out that for the flow of oil in the center of the capillary, the quadratic dependence works fine. Sorry. And we also estimated the effect of the wetting films. So this slide clearly demonstrates that thicker wetting films provide higher flow velocities of oil. This line represents the oil-water interface, while the saturation of the oil and water in both cases are identical. You can clearly see from the colors that the flow of oil, the velocities of oil are much higher in the right case. This happens because flow of water in the films kind of carries the oil drop. So in order to come up with macroscopic model, we had to perform 3 steps. First, we needed to account for more realistic distribution of phases within it, and this resulted in introduction of so-called saturation fractions or phase fractions. So we splitted each phase, water and oil, into a number of subphases. Also, we needed to determine a way to calculate the saturations of these subphases and the way to calculate the relative permeabilities for them. So in order to explain how we did it, I will do it step by step. So in the initial, at the start of the water injection, we have oil clusters that can flow and some irreducible water saturation. As we inject water, the flow of mobile water emerges, and the amount of water is increasing. But at some high value of water saturation, the trapping will start, which will form trapped oil, or oil ganglia as we call it. When we will start smart water injection, that may result in the mobilization of part of the trapped oil and the formation of mobile ganglia. And as we've seen from the microscopic consideration, the flow of oil ganglia is densely related to the flow of wetting films. So we also have to split the mobile water into water cluster and water films. So in total, we have 6 subphases, 3 phase fractions for water and 3 phase fractions for oil. However, we were dealing with tertiary recovery, and this allowed to simplify the system because this one had too many parameters that were not known. So we reduced the number of phases to 4. First of all, we assume that in tertiary recovery there is no active oil cluster. It also means that we do not allow our oil drops to come together to form an oil cluster. And also, as we are dealing with tertiary recovery, the water saturation is high, so immobile water does not make any difference. That's why it's not considered. The relative permeabilities for this model, we assume that for water and oil cluster and water films, some generalized Darcy law may apply. However, we immediately assume that for the flow of oil ganglia, we need to introduce something different, something that resembles behavior observed on the micro scale. And we assume that it's proportional to the flow velocity of water films and saturation of mobile ganglia. What we did next is we needed to estimate this proportionality coefficient. So what we did, we took a pore network model, a simplistic one constructed of angular pore bodies with similar sizes, and performed simplistic upscaling. This allowed to obtain simple relations between relative permeabilities and fractional saturations. And as you can see, the relative permeability of oil ganglia is proportional to saturation of mobile ganglia and relative permeability of water films. Also, there is some not very strong dependence on the saturation of active water cluster. And the parameters here, they might be estimated on the basis of microscopic considerations that was introduced before. And also these parameters, they are viscosity dependent. So it's also rather important for us that in reality what we obtain here is that relative permeabilities depend on viscosity, which is usually not considered by any classical model. The last step in model establishment was to determine how to calculate the phase fractions. And in order to do that, we performed simulations of the imbibition process in the Pore Network Simulator from Imperial College, London. So the results were something like this, and we come up with some simplistic model to resemble this behavior, which was inserted in the original model. With all this, we constructed a numerical model, and the most important about this one, I mean, the rest is more or less as we did the previous time. However, first of all, we were using the splitting approach, so we were calculating convection and reactions separately. And second, we used a second-order accurate scheme for numeric fluxes and used only 200 finite volumes. But because we used scheme of the second order of accuracy, it gave very good resolution of the results, which are presented here. So that is the particular reason why I was showing the solution for the tertiary chemical flooding earlier in this presentation. So it's represented here. This is the prediction of the conventional flooding. And here you can see that there is a concentration front of the chemical, and there is an oil bank that is formed, as been discussed, and this oil bank travels ahead of the concentration front. However, the prediction of oil ganglia model is different. In this case, the concentration front travels ahead of the oil bank. And so what will be observed at the effluent is first we will obtain the chemical that we were injecting, and only then the oil will arrive. Also, we study how the permeability of water films affects the displacement efficiency, and we found out that if we increase the permeability of water films, of course, we will improve the recovery. To illustrate this, I just plotted the amounts of mobile oils that remain in the system after 4 porous volumes of injection. So this is the base case, and this is the case with 2 times increased permeabilities of water films. And this is after 10 porous volumes of injection. Clearly better improvement of recovery at larger permeabilities of water films. So this can be again seen on this picture here. With high permeability of water films, we can produce all the mobile oil within approximately 8 or 9 porous volumes of injection. While with low permeability of wetting fields, we keep on injecting for 20 porous volumes, and still there is some oil that remains in the system. I'm sorry, this was the slide that this was the picture that I removed from the slide, but unfortunately it's still here for some reason. I don't know why. Lastly, we studied the effect of adsorption reaction kinetics and non-instantaneous oil release from the surface. And we concluded that if we account for non-equilibrium sorption, it will not delay the arrival of the oil bank, but it will slightly decrease the production. So the blue curve is the equilibrium absorption, while the black curve is slow absorption process, which means that oil is getting released relatively slowly. What can happen is that oil drops are released with some delay. For example, that may happen if there is a threshold value of the contact angle at which oil drop get liberated from the surface. And in this case, we can clearly see that such effect can delay the recovery for a couple of pore volumes of injection. And this behavior was exactly observed in some of the smart water experiments. What I mean is that in some of them, the incremental recovery was observed after 2, 3, 4 volumes of injection. And in some of them, even in waterbed system, the production from core plugs were continuing for 20 porous volumes of injection. So most probably I just said it. So the main conclusions of this study is that presence of water films on the surface of pores can facilitate flow of oil or oil ganglia, and this flow is relatively slow, so it can continue for a long time of injection. We can produce oil continuously. And also, if we account for non-instantaneous release, it can explain the behavior when oil is produced after a long time of injection. Lastly, I performed the analysis of some of the smart water flooding experiments in order to verify if certain mechanisms can explain them. And this study was concentrated on carbonates, and actually it was on the chalk, Stevens clean chalk. This choice was dictated by the fact that there is a large number of data available, including single-phase experiments, two-phase flow experiments, and so on. So these are the experimental recovery curves obtained here at DTU by Adil Zahid, who performed seawater flooding or flooding with seawater like brines in the oil-saturated cores at different temperatures. And on the left picture, you can see the secondary flooding performed with sulfate-free brine, seawater, and sulfate-rich brine. And we can clearly see that the performance of the sulfate-rich brine is better. On the right picture, we can see tertiary flooding, where first sulfate-free brine was injected in the reservoir, and then it was substituted with seawater or sulfate-rich brine at different temperatures. And again, what we see is that in all cases, when we were starting injecting brine that contained sulfate, we were getting additional oil. And the effect was also stronger with temperature. So we were curious if introduction of surface chemistry of carbonates can explain this behavior. This was dictated by the mechanism that was proposed by Thor Austad and his co-workers, which reflects the importance of divalent cations and anions such as calcium, magnesium, and sulfate on the recovery. Because carbonated surface is charged, these ions can absorb on the surface, and this may affect the intensity of the interaction of the surface with oil. So if it results in the decreased attachment of oil, the oil can get mobilized and removed from the system. Considering literature on the subject, I came up with conclusion that 3 reactions should be considered. 3 surface absorption reactions should be considered. So the first two represent absorption of calcium and magnesium on negatively charged surface sites on the surface of carbonates, while the last one is absorption of sulfate on positively charged sites. The main problem of this model is that the parameters of the model or equilibrium constants of this reaction, they are not very well determined, and the temperature dependence is not very well known, and there is a broad variation of parameters. The numerical model, in this case, I used BOSS simulator, black oil simulator, and I modified it to account for the enhanced oil recovery and these surface phenomena effects, just in order to be able to come to 3D later or perform more advanced modeling. So what I did first is I needed to get estimate on the parameters for the model, for the surface model. So I analyzed the flow-through experiments, which are the single-phase flow experiments performed by Strand et al. And here you can see the effluent concentration of sulfate. And here is tracer. tracer is not getting adsorbed on the surface while sulfate does. That is the reason why there is a retardation of sulfate at the effluent. And similar happens here on this picture, where the calcium concentration is plotted. Concentration of calcium are equal in the injected information brine, but we clearly see that there is a decrease in calcium concentration. And this is due to adsorption. This means that adsorption of sulfate facilitates adsorption of calcium. What was done is I just tried to fit the parameters and model these experiments. I just show a number of them. And at low temperatures, the fit was relatively well, while at high temperatures, it was a little bit less good. In all cases, for sulfate, the fit was, I would say, reasonably good. And the model was able to capture the fact that adsorption of sulfate facilitates adsorption of calcium on the surface. But the problem here is that we didn't catch, for example, this behavior, which is the long-term decrease in calcium concentration, and we were not able to come up with the explanation for this. Similar modeling was applied to study similar experiments with varying calcium concentrations. So here is the fit. I mean, I'm not saying it's perfect, but at least it's resembling behavior that should be there. And it demonstrates that also if we increase the amount of calcium in the injected information brine, we will increase the adsorption of sulfate. So this kind of proved that in what we observe in the experiments is a combined adsorption of sulfate and calcium and magnesium simultaneously. What was done next? With these fitted parameters, I calculated equilibrium surface concentrations for the injected brine in contact with surface, and I plotted this calculated surface concentration of adsorbed sulfate versus the recovery factor for the experiments performed by Adil. And I decided that this may be a linear correlation. So this was the assumption. I just suggested that residual saturation can be related to the adsorbed amount of sulfate with a linear correlation estimated from this picture. And this was the only parameter that was fitted. The rest of the parameters were obtained through the Welch method for only secondary flooding. And I performed modeling with this dependence, trying to reconstruct the experimental data. And you can see that it gives, in some cases, relatively good fit. What is especially important here is that it catches the transition zone relatively good. And this means that only modification of one core parameter, residual saturation, was sufficient to perform this modeling, which means that the flow of oil in this case was not controlled by some complex mechanism such as oil ganglia mechanism. But still, it might be that it could be observed even here because all these experiments were continued for a short time, only 4 porous volumes of injection. And we can see here that some of them were stopped after 2 porous volumes of injection, which means that if we keep on injecting for 10 porous volumes more, we could produce, I don't know, maybe 10 additional percent, maybe none. But this does not prove that oil ganglia mechanism is not relevant. Finally, this slide shows the effluent concentrations of the calcium, magnesium, and sulfate during the two-phase flow. And we can see that it resembles behavior similar to those in this single-phase flow. I mean, we observe the reduction of concentration of calcium and magnesium, and by comparing the retardation of each of the sulfates of the ions, we can decide which one has higher affinity towards the surface. That's why I consider it important that when we perform smart water flooding experiments, it's vital to measure the effluent composition, just in order to be able to see what's happening in the system. So these are the main conclusions of this study. The introduced surface chemistry model was able to capture at least qualitatively all the effects that are observed in the experiments. Quantitatively, the fit was not always very good, while the fitted parameters provided a good match of the experimental data and with simulated curves. The overall main conclusions of this study is that, first of all, dissolution of mineral and volumetric non-additivity does not have a significant amount on pressure or flow in porous medium. It's a negative, but also an important result is kind of cutting off something that is not important. Now, the second is that our model considering the flow of oil ganglia. It states that oil ganglia can mobilize due to formation of wetting films and flow due to the viscous forces on the oil-water interface. And this model can explain behavior when when incremental recovery is observed during a long time of injection or observed only after certain pore volumes were injected. And lastly, in some of the experiments in carbonates, namely the Stevens-Klinchok, correlation exists between the residual oil saturation and the amount of adsorbed sulfate. And I'm not sure it can be more generalized. I mean, it's a statement about Stevens-Klinchok and particular experiments. And yeah. So there are some ideas for future work in this area. First of all, I think it's important to consider oil-rock interactions, as this can be achieved through the surface complexation models of the oil surface. The main problem is that it will involve a number of poorly determined parameters, so I'm not sure it's worth it. Second, from my opinion, more attention should be paid to the microgeometry of the pore space, and we should introduce something like, for example, pore size distribution in the modeling somehow. And I see the possible ways to do it is to perform new network modeling, pore network modeling, or there are also continuous mesoscale models which can be utilized for this. If we are going to develop it into business, to go to industry with this, of course we need to do the model in 3D, heterogeneous and fractured porous medium, just to see the effects that comes from these 3D models. And in engineering applications, full geochemical model is required so that we can estimate, for example, the effect of dissolution on the effective concentration of ions and how it will affect the surface chemistry of the rock in turn. So thank you for your attention, and I would like to express my gratitude to my colleagues and friends, and most of all to my supervisor, Alexander Shapiro. So thank you.
Thanks, Artem. It was a perfectly timed defense, exactly 45 minutes. We now will take a 2-minute break, after which we'll continue with the